Good morning and welcome to the Space Madness podcast. This is your host, Jeff Nasanov, and your co-host, Wednesday the Cat, always here. And today we've got an interesting guest. His name is Chad Pozarycki, a recent graduate of Georgia Tech with a Ph.D. in chemistry. And I forgot the intro. We Space Madness podcast because space exploration is maddening, and I'm sure no less than getting a PhD in chemistry and the many years of work it takes and the uncertainty involved in the entire process. So we're going to get through all of that today. So Chad, if you could introduce yourself briefly.
Yeah, sure. So as you said, I just finished my PhD in Amanda Stockton's lab at Georgia Tech. Basically, I've been working the past 3.5 years on astrobiology. So looking for ways to detect life on other planets. And what that's looked like is me going into the field and collecting samples from a bunch of places that have chemical or mineralogical similarity to other planetary bodies in the solar system. So that's what I've been doing lately for the past few years. Before that, I was at NASA Goddard. And then, so that's what I've been up to.
So you worked on the 2020 rover at Goddard, right?
I worked on Curiosity.
Curiosity. Okay. Even earlier. Yeah. When I was the one from 2012.
Exactly.
So there's a lot of questions that I would start with anybody with that background, but I'm curious at what point in your life did you decide that this kind of thing was what you wanted to do? Because it's not a decision you make lightly, and certainly sets you on a long path.
Yeah. Well, I think for me, as much as with most people, the space program, the human exploration aspect of it was what caught me as a child. I started going to Kennedy Space Center, to the Visitor Center, when I was 2 years old, and my parents would bring me back there every year. And so, until I was like 12 or 13 years old, I had consecutively gone to Kennedy Space Center every single year, which was I think the large first investment in my education.
Yeah. Well, that'll do it.
Yeah. And at that point, going into middle school and high school, I was totally into engineering, and I wanted to go be an aerospace engineer. And so I got to high school and I was talking to my guidance counselor, and I said, hey, I want to be an aerospace engineer. Are my grades good enough? Like, what university should I go to? And the guidance counselor said something along the lines of, your math scores aren't very good, so I wouldn't recommend engineering, which understandable, right? And so instead, they recommended I do astrophysics, which obviously doesn't require any math knowledge at all. So they said, oh, your physics score is good. You're in AP Physics. You should go do astrophysics instead of engineering. So I went to Penn State, which is also where my father went. And I was really resistant to it because I had never heard of Penn State. Everyone in high school tells you need to go to the Ivy Leagues, you need to do this, that. And I think, after going to a state school with a really great astronomy program, that was the best place I could possibly have been. That was an awesome experience. Yeah, that's the childhood education portion of the history.
Well, I can relate because I went to the Griffith Observatory a lot more often than once a year because it was right there in LA. And it just put a perspective in me, or it set me up with a perspective that I never really could look beyond. In fact, to the extent that more fundamental basic things about everyday life seemed mysterious, more so than they actually were, because I was applying a lens that really didn't need to be applied on it. And so as I've gotten older, I've observed that with some amusement. So what's the curious looking device behind you there?
Oh yeah, that's a good question. So this is something that I worked with during my PhD. I didn't build it, actually. A previous grad student built this, and it's been part of an iterative cycle over decades of trying to make chemical detection as small, as lightweight, and as automated as possible. As I mentioned earlier, astrobiology, we're looking for signs of life elsewhere in the solar system or in the universe. Our lab focuses on, Amanda's lab has been focused on for the past, decade or more, basically capillary electrophoresis, and a number of other technologies used for detecting biosignatures or small chemical compounds that would be evidence of life if found on another planetary body.
Okay. So let's unpack that term, capillary electrophoresis.
Yeah.
What does that mean? What does each of those words mean, and then what does it mean together?
Right. So a capillary is a very small channel or a thin tube through which, in this case, a liquid is traveling. And then electrophoresis, the electro part is you're applying a voltage, and phoresis I actually don't know the Greek or Latin root, but I imagine the phoresis means you're separating things. And
Okay.
so electrophoresis is the process of taking compounds that are in a mixture and pulling them apart so that they arrive at your detector one by one. And in chemistry and analytical chemistry, which is what we do here, the most important part is making sure that you can identify those compounds individually, specific about what you're detecting. Because if you're not being
Okay.
specific, then you could be detecting anything. So
So
making sure,
I thought I knew what that was, but the way you explained it there was really interesting. That the process of separating molecules, atoms,
yeah,
proteins,
molecules in this case.
molecules. So you detect, so they reach the detector one at a time. That strikes me as a fairly important detail when you're not sure what you're looking at. Is that
Yeah.
fair to
Yeah.
say?
And so, I'm using a bit of a metaphor here by saying one at a time. What I really mean
Uh,
is each different compound is arriving. And when you look at what we call a chromatogram, or with
mm,
electrophoresis an electropherogram, this is sort of getting a little bit into the weeds. What you see is just
sure.
a series of peaks. Instead of looking like just a straight line, they're usually a Gaussian. So what that
Mm,
represents is you have sort of this packet or this cluster of compounds. Let's say it's the amino acid alanine. So you have a bunch of alanine molecules in a liquid, say it's water,
mm.
and it's arriving or passing the detector over time. And that Gaussian curve is essentially the stack of those compounds crossing over time. And so that's what we're talking about when we say chemical separation, is we want to get those Gaussians spread out. We want to make that mixture spread out so that we can A, see what each compound is, and then B, measure each compound individually.
Okay, and the reason that I would guess that the reason that the compounds arrive separately is because of the different masses that they have or charges, and
Yeah,
that results in sort of like I'm imagining like a centrifuge will separate things because they weigh different amounts,
yeah,
to be overly general.
yeah,
Applying the same force will separate things by mass.
yeah.
So same basic idea, just a lot smaller.
Yeah, absolutely. I
Okay.
think, yeah, the general concept is that as chemists, we're not interested in as much the amalgamation of things, but
Okay.
the specific components of it. We try to break things down and understand them and why each of these pieces make the whole and make the whole behave how it does.
Okay.
And so in chemistry, whether it's atomic physics, when you're separating isotopes of uranium, for instance, during the Manhattan Project, or if it's in a chemistry lab where you're trying to look at steroids in an athlete's urine, all you're doing is taking things that have different properties and using those properties to pull them apart and look at them individually.
Okay.
Yeah.
So to I'm glad you gave a couple of examples of different types of samples. So the obvious samples of interest to this audience probably are the samples sitting in tubes on the planet Mars. So
Yeah.
it seems to me that a device like that, you would return those samples from Mars, or somebody would, and very carefully put some of that in, I'm guessing the top circular thing.
Sure. Yeah.
And so a device like that would be the next step for samples returned from Mars. Is that right? Or
So
among them, among the
yeah,
options?
among the many steps. So
Okay.
I have some friends that are working on the Mars sample return receiving facility
Mm,
concept and what's going in it. And a lot of those folks, some of them are at Goddard, some are at other institutions, are like NASA Johnston, for instance. They think about not only what instruments are we putting these samples into, which
mm.
ones are going to get the most information out of the samples, but also how do we keep those samples clean? How do we prepare them so that we're getting a uniform kind of information out of each of the samples? How do we make sure that those samples don't contaminate Earth life, which is
Mm.
planetary protection, whole big
Yeah.
conversation we can have about that. And so, yeah, realistically, what you would see is probably some kind of capillary electrophoresis being used for the analysis of the Mars samples. Now, it wouldn't look like this because this is a prototype system or a benchtop system that we use for development of spaceflight instrumentation, but it
Okay.
would work on the same principles that I described.
Okay. So one of the most interesting things to me about the Apollo samples that I only
Mm.
recently learned actually was that apparently they kept a bunch of them deliberately in storage for future instrumentation
Yeah.
that didn't exist yet. And
Yeah.
And while the whole Apollo project was remarkably forward thinking on its own, I found that little detail to be especially so, recognizing in the 60s or 70s, well, we don't really know, we know we will have much better instruments in the future, so we better
Right.
save some of the stuff. So,
Yeah.
and that was many hundreds of kilograms of rocks, I believe.
Yeah.
So on the speaking of this, of the sample return planning, I mean, is there consideration of the fact that someday this thing behind you will be obsolete and almost
Yeah.
laughable?
Absolutely. I think, you could even make an argument that it is already obsolete in some senses. And so there's a lot of attention paid by current sample return missions, including the
Mm,
OSIRIS-REx mission, to store a lot of samples for future
mm.
use. And just as an example, when I was at Goddard in the astrobiology analytical lab, I had the incredible privilege to hold a bag of samples from the Apollo program that were shipped to
Wow.
Goddard. And so this is exactly what you're talking about. There were chunks of moon rock that were sitting in a glove box in a vault at NASA Johnson. And, someone at Goddard and part of our team basically ordered some out or was part of a proposal to have it shipped out. And one day I was sitting at my desk and Hannah McLean comes in and says, "Hey, Chad, let's head to the mail room. We got to pick up a package and I need a witness with me while we're transporting the packages across Goddard's campus." And
Wow.
so we hop in the van, we drive across, and just a couple signatures, and I'm holding a box of moon rocks in my hand in the back seat of the van as we drive back.
Wow.
So that was a cool experience. My only
See,
role was basically carrying them and putting them in the vault. But
I mean,
it
witnessing
yeah,
the moon, I mean, what more philosophically meaningful role could a person play other than maybe standing on it?
yeah,
That's amazing. That
yeah.
so
I like to
you
think
you
that, yeah. No, I
no,
was
go
going to say, I
ahead.
like to think that during that time when I was holding that box that I looked up and I saw the moon and the daylight standing there and but I think I manufactured that memory,
Hey, you're only
but
human. That's
right.
that's natural. Wow.
Yeah. But,
So,
but then as you were saying, we used instruments that did not exist in the 1970s to
yeah,
analyze those samples. And so Jamie Elsela did a lot of good work on those samples, presented at LPSC the following year, and was looking for organic compounds in those lunar samples. So that's the whole story of exactly that example
sure.
being realized.
So how does the scientific community decide when dealing with such a scarce resource and precious resource?
Yeah,
How do they decide when is the right time to put some of it at risk,
a good question.
basically?
You know, I I'm not an expert on what goes out of the lab, gets sent out, and what the criteria are. But I
Mm,
will say, having looked at some of the proposals and considered writing some proposals, they're called LARS proposals, or
mm.
laboratory analysis of return samples. Those are essentially where you say, "Hey, we have a new instrument and we want to test it
Ah,
using these samples." And some committee says, "Yes, this is interesting," and then they approve the grant, the money for the grant, and then it goes, I imagine, to NASA Johnson or whoever holds the samples,
mm,
and they say, "Okay, it's been funded. This is a lab that's credible, and they have a plan for how they're going to manage the sample. It's only a very small amount. It's going to
yeah,
yield this sort of science return." And so you have to trace it all the way through the proposal. You need to be able to say, "We're going to use exactly this amount. It's going to do this extraction. We have this much, sort of buffer room, 10% or
sure.
whatever. This is exactly what questions we want to answer. We're not just going to say, oh, it's open-ended."
Right.
As you know, with mission design, you need to hit targets for what questions we think we're going to answer, as annoying as it is.
Yeah.
So,
So the device behind you, well, so you mentioned, I think, the key, which is having a new instrument is probably a pretty solid argument for using a finite resource like that, right?
absolutely.
So I guess if you could tell me the cycle sort of how these new things come
Yeah.
to be sitting on a desk like that. I mean, you mentioned that was
Yeah.
already obsolete. I mean, at one point it was presumably science fiction. Can you
Yeah.
walk me through that?
Yeah. So, instrument development sort of goes along the scale of technology readiness level to a
Mm.
certain sense, which I'm sure you're familiar with. And, for the audience members, it's a way to measure how ready a technology or a tool is for application, either in space
Mm.
or, I think the defense industry also uses this for their applications. So, TRL is just a way to measure how ready is your instrument in this case. And so what that looks like is you start with a napkin sketch and you're
Mm.
sitting at a conference and you're talking to your buddies and saying, hey, I think we could probably measure this compound if we use this fluorescent dye, or, we could use this kind of laser instead of that kind of laser, or we could dampen this signal so we could see this signal instead. And
Mm.
that's all in TRL1. When you get to TRL2, what it looks like is now you're actually drawing schematics. Now you're
I don't mean
thinking
to
through the
interrupt you,
math.
but I just
Oh,
want
yeah.
to, for the audience, I love the way TRL1 is written by NASA. Basic
Mm.
principles observed and reported.
Yeah.
And
Yeah.
I always got a kick out of that because you could put almost anything in there that doesn't, well, by definition, doesn't violate the laws of physics,
Right.
or at least not too much.
Yeah. Yeah, exactly. And so even, at that point, the napkin sketch might even be TRL2, right? When you're,
Mm.
putting a box around something, that's probably getting towards TRL2. And so if you're working on schematics, if you're prototyping something in a very, very small scale, you're moving up 2, 3, 4, and 5 is kind of what you have behind me. This is something that it does what you want it to do. It detects organic compounds. It might not do it super consistently. It might not do it in really large scale. I can't pump 1,000 samples through this in one day. I guess I could, but I would probably collapse at the end of it. But then you get to TRL 6 and 7, where you automate things, you make them streamlined, you get the software running to make everything work
Mm.
in concert. And more importantly, you start putting it in environments that are relevant to where you want to send the final product. And so what that means is either the samples that you put in it are relevant, or the place that it exists in is relevant. So you
Right.
could bring this, for instance, like JPL took a version of this instrument to the Atacama Desert. They call it the chemical laptop. So Peter Willis's group took a capillary electrophoresis instrument out there, and they were doing analyses of samples that you could take, just feet away from the instrument.
Okay. So the TRL game was one of the most interesting parts of my NASA experiences.
Yeah.
Is to convince NASA that a mission is ready to fly, you have to have fairly high TRL, which itself can only come from previous funding efforts,
Yeah.
which itself comes from achieving lower TRLs.
Yeah.
And so, the name of the game in space exploration is managing risk, not minimizing it, but managing it. And so there's a constant tension in mission design between wanting to do something ambitious, to do some new science, but also managing the risk so you actually get something back. And
Yeah.
and that never ceased to be fascinating in my many years of working with organizations to get missions funded. And I've seen
Yeah.
arguments on both sides of the absurdity scale too. And it's a really interesting
Yeah.
experience. So
Yeah.
can you walk us through another level deeper of just how that device works? I think that,
Mhm.
we've kind of talked about the physical principles in the abstract, but
Yeah.
I think the audience will be interested in just how it works.
Yeah, absolutely. Even before that, I just want to mention what you said about risk. Something I learned at Planetary Science Summer School at JPL
Mm.
is not only are you managing risk, you're paying for it. And so
Yes.
if you're low on money, you can't choose the TRL4 instrument. You got to choose a TRL9 instrument.
Right. And I really like that you mentioned the Planetary Science Summer School, which is
Oh,
an
yeah.
amazing thing. I'm so glad
Amazing.
it's there. Any student should look into it. And I had a guest earlier, Jason Durla from NASA headquarters in Goddard, earlier this week, who shared a really interesting observation about the budgeting and the management of risk, as you said. And it was basically this, that the risk in space is infinite. And you have a finite budget, but and you only get in trouble usually if you go 15% over budget.
Mm.
And what that means is that in the calculus that results from that, you are incentivized to go 114.9% over budget in
Yeah.
order to manage the infinite risk of the space environment. And so
Yeah.
it's an interesting philosophical question of squaring those two things.
Yeah.
In
Incentive structures.
yes,
Yeah.
in the daily management of a project and risk and so on. So
Yeah.
let's get into
Yeah.
the hardware
The instrument.
then. Yeah.
So this is a benchtop system that was built by some former members of Amanda's lab, and which I used for some experiments. And the way it works is you have sort of two major components. You have the optical system, which is the detector, and then you have the separation system, which is the capillary and the high voltage that's applied to it. And so the goal of the instrument is you take a sample and you separate that sample and you detect compounds in it and get information on the concentrations of those compounds. And what that looks like, as a process is I will take my micropipetter, because this is a benchtop instrument, so we don't need to have an auto sampler. We don't need to have a ton of super precise ways to get things in. You can have a lab tech working on it. And you take the reagents. I have them just sort of sitting here in centrifuge vials, and I'm going to pipette them into some holes that we have on the top of this disc here. Now, what sits in this disc is essentially a very thin piece of glass. And on that piece of glass, there are little channels, and each of those channels has a hole at the end of it. And so what we're doing is we're putting liquid into those holes so it can flow through those channels. And underneath that channel is where this detector system is sitting that you can see here. And
just a quick question. The holes, I'm guessing, because I saw Morgan Cable's lab at JPL 15 years ago. I'm guessing that the holes have some role to play in managing droplet size so it flows, something like that. I remember those things were always jammed. That's all I remember that from. And so that's where I met Amanda in that lab in like 2011 or 10.
Okay. So one of the hugest issues that even when I was explaining, the liquids running through the channels, I was in my head, I was thinking, but you got to deal with bubbles. So, the very last thing you really want is for it to be a droplet, Obviously droplets are coming in, and in some contexts you actually do want droplets to exist so you can mix things. But in the capillary electrophoresis system here, which is super simple, you're not doing any mixing. If you have bubbles or air in any way, you're having a bad time, because you're not able to complete that circuit and actually cause that chemical separation effect.
Oh, because there's an air gap across which the voltage doesn't.
Precisely.
I don't know the word arc.
Yeah, the voltage isn't going to break down. There's no, we're not exceeding the breakdown potential that there's going to be a bolt of lightning and connect. So for instance, what we have also, I can tilt my camera a little bit.
Yeah.
Over here, you can't really see it, but back here is a high voltage mixer. And so what you have is a system that allows you to adjust the voltage that's coming in to this system. And here are a couple voltage leads that we plug into the top of this system.
Depending on the amount of voltage you want, which determines this amount of separation.
Exactly.
So just like I'd imagine a heavier molecule needs more voltage. Is it that simple, or probably not that simple?
So it's actually, if you're thinking about a different technique, a different analyzer like mass spectrometry, you would actually directly correlate the mass of the atom or of the molecule to the amount of field strength that you're using. But in a situation like this, you're actually separating the size and the charge. So mass, of course, is correlated with the size, but what we're doing is there's more hydrodynamic and more, I guess, liquid chemistry going on at the small scale. So what you're doing is you are taking, bigger compounds and smaller compounds and turning them into faster and slower. And the way that you turn big and small into fast and slow is by applying one uniform voltage across and basically saying, you can only accelerate the small ones by some amount versus the big ones. And I'm simplifying to a certain degree. If you're a capillary electrophoresis expert, you're going to tell me that I'm doing this explanation all wrong. But the most important thing I think that you get out of this system, this idea, is that you have a separation part that's really important, because it tells you something about those compounds, and it tells you their relative properties. So if something comes out before something else, that means that it is more small or more charged than the thing that comes out after. And when you're learning about the environment, that's very important.
And by after, in the sense of time, you're talking about moving over the detector.
Precisely.
In that flow we talked about earlier.
Exactly.
Yeah.
And so when you get go ahead.
No, please.
Yeah. So when you get to the detector, you have this laser here, and it essentially shoots a laser beam to this dichroic mirror that reflects the laser beam up, that hits the compounds. I glossed over this, but there's some sample preparation involved where you fluorescently tag your compounds. I won't go into detail about that. But you have a fluorescent tag so that when the laser hits it, that fluorescence occurs. The fluorescence is at a different wavelength than the laser. It gets sent down through that mirror, and because it's at a different wavelength, it can pass through a filter lower down and get into the detector. And that's how you can exclusively detect the light from the fluorescent compounds. And
Okay.
that's basically the whole process.
And for the audience, the fluorescence part means you attach a molecule or something like that that shines in response to certain wavelengths, correct? And then
Absolutely.
that's what you're actually looking for. You're looking for it like you're not actually seeing the molecule as much as you're seeing the tag glowing that tells you the molecule is there, right?
Exactly.
Okay, good.
Exactly.
I remember this stuff.
Yeah. Yeah.
Okay, cool. So what does so suppose you had a blank check to make this system better. What does the next version of this look like?
Yeah. So as I said, I said something about this being obsolete. What I really mean by that is what you can do is if you've already used this system to develop, the sort of chemical methods that you need to, because this has a lot of use in that it is really big and you can adjust things super easily. You can just put your arm in with a screwdriver and it's a piece of cake. You can get it to a point where it's much smaller. And that has its benefits, of course, because it's closer to something that someone might want to use because it's small, but it has its downsides because you can't really tinker as much as you can with something like this. So if I had a blank check for development, what I'd do is say, okay, let's take this to a smaller form factor and let's improve the number of tests that we can run on it and improve the different kinds of chemical analyses that we can do with it, increase the complexity of some of the sample handling. I'd remove the Chad pipetting aspect of this and I'd turn it into, maybe there's not necessarily a robot arm, but just a port that you put a sample into. And then once it goes in, there's a microfluidic computer that does all this analysis for you. And that's a lot of the stuff that JPL and that Amanda has been working on for the past couple decades.
Okay. So how does this device, so one thing I've always liked to try to do is explain what the rovers are doing on Mars to people.
Yeah.
And, the inside of a rover on Mars is a pretty abstract thing for people to imagine. Is what you just described, a smaller version of this, is that the kind of instrument that is on the rovers now that certainly I can guess we'd like to put it on future systems?
Yeah. So what we have on for instance, a Curiosity rover is an analytical chemistry suite. It is a wet chemistry analysis system and something that can look at organic compounds in a specific way and quantify them. But it's not using this technique. It's using a technique called gas chromatography, mass spectrometry. So instead of separating a liquid through a channel, you're separating gas through a channel. And that requires high temperatures and it's complicated in different ways. But the reason that ended up flying to Mars instead of this is because the TRL, the readiness was essentially higher. And so the amount of risks that you need to retire before you launch an instrument go way up if you have a low TRL. And if you were to send something like this, which was actually suggested, the Mars Organic Analyzer was suggested, the Matthews group, and I imagine some folks at JPL were involved in that back in the early 2000s, and also the URI instrument suite, which I think was originally going to include something like this on the Rosalind Franklin ExoMars rover. But in both these cases, it was either not selected or descoped, and so capillary electrophoresis has not yet flown to space at all, from my understanding. Say we, but my academic ancestors have proven out a lot of the necessary, works in microgravity, works in long-term storage, works under, vibration, all that. But it just hasn't had the opportunity to beat out, which is essentially the heavyweight champion, GCMS, gas chromatography.
Sure. So this is reminding me, and you're of course reminding me of the TRL is a harsh mistress. For lack of a better, there's a lot of ways to say that, but that really does drive. I mean, it should drive, but when it's boiled, when all that work is boiled down to a number, it's sort of a stark thing to have say, well, we can't convince NASA it's a 5, so we got to go with this, and at a certain point, these things have to be quantified. But you reminded me of this, what I thought was a good idea very early in my JPL career, as I started to understand the various subsystems in a spacecraft and all of the different parts, or not all of them, but many of them. I thought, well, why don't we just make a Amazon.com for space hardware that lets people basically assemble spacecraft conceptually and all that. And James Smith at JPL, to his credit, he sat there and listened to me for 20 minutes. And then he said, where are you going to get all that information? And I thought, oh, right. And of course,
Yeah.
I then spent the next 10 or 15 years trying to put together these stories that use that honestly but persuasively use these different properties and in some cases unknowns and known quantities to
Yeah.
make a compelling case for a certain mission. So
Yeah.
so
And for a certain instrument, it's important that you're comparing apples to apples. And
yes.
if you're not looking at an Amazon, they have the comparison, check those boxes and you could put it in, a
Yeah.
list and see all the specs compared. If you're
Yeah.
not doing that with your instruments, then you're going to get a pretty poor story.
Yeah.
I think the issue when it comes to TRL is that it's a really good metric and it's actually a better metric than any other way to judge an instrument has. If you're judging an instrument by its capabilities, instruments are all very different and you can't compare, the temperature capabilities of a GCMS to the temperature capabilities of this instrument because temperature is less
Right.
relevant chemically than it is for GCMS, which needs to volatilize compounds. And so, for instance, if there was a number that told you how good is this instrument at doing, this hypothesis being answered or this
Yeah.
hypothesis being answered, that might be a good way to really apples to apples compare. Because if you have an instrument with a really strong TRL, it's going to win a lot of the time.
Yeah. Which and then can then actually change the science goals if that's necessary
Yeah,
for the whole mission design to close.
absolutely.
For example, this may be. I would imagine if you think you have amino acids, you probably don't want to volatilize them, right? You don't want to burn them up in order to
So
see
it
what they are.
depends.
I mean,
It depends on your strategy. In GCMS, what you do is you add a derivatization reagent, or basically just like that fluorescent tag, except instead of causing fluorescence, it's causing the amino acids to be volatile. And so you volatilize the amino acids with that chemical reaction. The compound is called MTBSTFA, which is the longest acronym I've ever had the privilege of learning in my first summer internship at Goddard. But basically what you do is
hold on. What is it short for?
methyl tert butyl silyl. I can't remember the whole
You
thing.
could have said anything and I would have nodded.
Yeah, but I know there's people that could check me on it.
Sure.
But I've had the privilege of being able to copy and paste the full compound name.
Sure.
But basically, to digress for I guess
Please.
zoom in for a little bit on the wet chemistry reagents on the Curiosity rover. You have TMAH and MTBSTFA. And the two of these, their job is actually to volatilize compounds to make them more readily detectable. Now, what you're asking is, do you want to volatilize compounds? With amino acids, I would think maybe you don't want to. I would agree. I think amino acids are easiest detected in the liquid phase. And if we're going to detect amino acids and the concentrations that they are at in the environment, which I think is an important question, biosignatures have a lot to do with patterns. And if you have different concentrations because of, volatilization and things like that, you don't really get the patterns as well. So this is something that you have to weigh. If you're going to GCMS, which is a higher TRL instrument, you have trade-offs where amino acid detection, fatty acid detection might be hindered because you need to add that extra step of prep and volatilization. Now, you still have sample prep here where you need to fluorescently tag amino acids, and a similar thing with carboxylic acids, but it's in the liquid phase. And so there's been different benefits to that.
Well,
now,
one of the most interesting things about all that sample preparation, I just want to zoom out for a moment and then zoom right back in for you. But understanding that these rovers on Mars are doing that automatically, that there's little tiny mechanical systems in there that are mixing things that came from Earth and are stored in little tubes, presumably more robust than that little plastic tube you showed me earlier.
Oh yeah,
just absolutely amazing. And when you see, I got to sit on one of the design reviews of MSL. No, one of those instruments. And just to see the mechanical drawings of them, this incredibly precise machinery, it makes a Swiss watch look like an elephant rampaging. I mean, it's just an amazing thing to see what humans are capable of. I never got tired of it. But back to you and zooming back in.
Well, I'm glad that you zoomed out for a second there, because I think the very important topic that I wish people knew more about is how difficult sample preparation was. And when I was at Goddard, Charles Malespin, who works in planetary environments, is now the PI or co-PI of Sam.
Sam being the
sample analysis at Mars instrument, the
yes.
gas
Okay.
chromatography mass spectrometry
Okay.
instrument
Sitting on
on
Mars right
Curiosity.
now, operating.
Yes.
Okay.
So he, when I was going off to grad school, I was asking him what projects he thought would be relevant, what I should concentrate on. And we sat down and he talked about sample preparation for a while. And even after I got to the school here at Georgia Tech, sent me a couple emails, and we were going back and forth about sample preparation is really the hardest part of detecting life on another planet. The hard part is you're not taking a liquid sample of amino acids and analyzing it like it's a standard in the lab. You're not taking a gas phase mixture of it and just volatilizing it and sending it through the instrument. What you're doing is you're taking rocks that are billions of years old, crushing them up, incinerating them, and then at the same time doing a chemical reaction with them and analyzing them. And most importantly, you're doing this with rocks that have never been analyzed, Earth, other than, of course, the meteorites that have come from Mars, which are somewhat different. And so there's so many question marks, so many complex reactive chemicals that make it difficult to do those analyses. And that's why we go into the field, and why we not only test our instruments with standards that we make in the lab, but with things that are real.
And, I'm so glad you said that, because that connects some dots for me. I saw your lab and I saw that cool freezer full of chunks of glacier and stuff. And I can only imagine the challenge of, I would assume what you have to do is find samples close enough to what you expect to find on other planets based on our current knowledge of the solar system, and try to find those apples to apples, in the not even an orchard, because an orchard is mostly apples. The apples to apples in a Trader Joe's or something like that.
Right. Exactly.
Wow.
Yeah. And the really tough part is not only, getting funding to go out there, get the samples and bring them back, but when you bring them back, and this is the hard part for me, is that's where the fun kind of ends at that point. And it gets really complicated and it gets really hard, because you need to decide on what story you're telling. Just like proposals, scientific manuscripts are stories that are getting across information to people. And as much as you want them to be true stories, or as close to the truth as possible, you still need to choose to include or disinclude things in order to effectively get your message across. Whether you're a good scientist or a bad scientist, you're making choices about what you include and what you don't.
And that depends, and for NASA, from NASA's point of view of how to get things actually funded and done, I mean, that actually starts at the other end of asking of what questions you ask when you're designing a mission, and having to decide how compelling can you be that we can answer this science question with this mission, with this spacecraft to this destination, with this instrument, all of which has some uncertainties and unknowns, and instruments work better within a certain range of conditions, but they might work okay outside of them, but then you have yet another. So it's a never-ending kind of balancing act. I always found it very interesting. On the complete other end of what you're doing.
Yeah, I think it's, having gone through planetary science summer school, which I will again say is one of the most incredible experiences of my professional life, or even just my life at all. Like, it felt like a vacation. It felt like super fun. That was a way for me to see, why did those decisions get made the way that they did? And it made me feel a lot better about it, because I understood that actually, no, people weren't making the wrong choices. People are making the choices that they have to with the money that they have. Every mission is going to be, let's scrape as much as we can together and put it in and stuff it into this package and make it the best looking story possible. None of these are sort of middling missions that don't have everything.
Everything's
the
a
only
compromise.
missions you see, the only missions you see are the best missions that were proposed, that there's survivorship bias, that everything that flies has got basically on the cutting edge of what is possible. They're the last thing possible. The most impossible thing is usually what gets selected.
And I had a conversation with Lou Friedman earlier this week, and it was really interesting to hear his perspective after many, many decades since the very beginning of the space age. And he had a slightly different perspective. He said every groundbreaking mission is actually a compromise, is actually downscoped from the initial version.
Yeah.
And thinking back to the missions from way before I was born, Pioneer, Mariner, and Voyager, these things that to me, and I imagine to you,
Mm.
represent just these incredible leaps into the cosmos. To go look at the history of them, like, oh, actually,
Yeah.
yeah, this was like half of what they originally wanted to do.
Oh,
You
yeah.
know,
Yeah.
and then to be involved in some of that work in the present or the recent past, and demystifying the sausage making, so to speak,
Mm. Yeah.
it's been really interesting. So
Yeah.
what's next for you?
So I'm working on a startup right now, which basically takes an instrument like this and puts it in your house so that you can analyze your own urine, and it will tell you about your wellness state. And hopefully someday it'll be able to tell you whether you have diabetes or cancer years in advance of any other technology. And so that's based on a field of science called metabolomics. And it just involves keeping a model of the biochemistry happening inside of you. And then
Hmm.
whenever you go off nominal or whenever you change from that, it detects it and suggests this could be caused by this disease or this illness.
So it sounds like vastly increasing the time resolution of your checkup and your blood work, and to an extent
Yeah.
of and accelerating, well, and increasing the forecasting time for when you actually might have a systemic issue.
Yeah. That's a really good way to put it. It's not necessarily ever going to replace, a doctor looking at a tumor or a doctor
Mm,
looking at your CGM data. But what it can do is it can recognize patterns,
mm,
and it really uses super rich information that comes from your biochemistry to understand the cycles and the patterns that your body
mm.
exhibits in response to exercise and nutrition and illness. And
Y-
so that's the idea.
Yeah, it always seemed to me that we waste a lot of information down the toilet
Yes, yeah,
and
we absolutely do.
down the
A lot
shower
a lot of
drain, and
companies yeah, a lot of companies are already on this concept that
okay,
basically taking data in from whether it's solid waste or
yeah,
urine or blood,
or
you
even like
know
brushing your teeth and spitting in the sink. There's got to be
Mhm.
useful information in that
Yeah,
stuff. I mean,
yeah, no doubt.
maybe I can imagine a future where there's some kind of very low cost detection systems in each of those things
Yeah,
that kind of like how my watch tells me how well I slept.
yeah,
I don't really need it to tell me that, I don't think. Well, there's a bias. Maybe I do need it and I don't know that, but then of course there's the balance of something my wife reminds me often when I talk about technology is, are you going to measure things that you have no intention of addressing, of getting too much information, basically? So
yeah,
it's a interesting philosophical and practical balance. For example, I know you can go to Turkey and get like a 3-day full intense checkup and get an MRI of everything. And what do you do with it?
what does it
So,
tell you?
so
Yeah,
yeah, so it's an
yeah,
interesting world now where you have
there's lots of information.
potentially access to huge amounts of information that many people will want to sell you that
Mhm.
may not have an immediate action you can take. So I imagine
Yeah,
that will be a big discussion in the near future.
absolutely.
But
Yeah,
with
I
what
think
you're doing, it sounds
yeah,
like it's a very valuable intervention, very valuable to alert of early interventions
yeah.
for issues that are, plaguing half the population already.
Right. I think, yeah, the key point that we're really trying to address is that there is no advanced chemical monitoring system in the market at all
Mm,
that does monitoring of what we think is relevant. There's amino acids that can tell you essentially about hundreds of different disease states. And these amino acids are not being tracked on a daily basis. We are creating something where you can track them on a daily basis and make it cheap enough that everyone can do it.
yeah.
And
Well,
so, yeah,
and I think targeting the blood sugar issues and possibly cardiovascular
yeah,
issues certainly seems like a great start in
yeah,
the United States today.
yeah.
So I want to thank our guest for joining me today. This has been utterly fascinating, and as it always is with chemists, my weakest subject. So thank you again for joining me, and
Thanks for having me. This was a great experience. And it was, I mean, it's always just great talking to you. So
likewise, yeah,
this is awesome.
cool. Well, and thank you to the audience for listening. This is the Space Madness podcast signing out, and we'll talk to you next time.